Hi folks, Mr. Keeley here with a lesson on intensity and the inverse square law. Today's big idea is that intensity decreases with the square of distance to the source. Let's make that make sense. I want you to think about looking at a bright light and then slowly moving away. What is that experience like? Well, when you get close to it, right, it's real bright. Maybe it even hurts your eyes. But as you back away, its intensity diminishes. It goes down. It decreases. From a distance, the light isn't so bright it makes your eyes hurt. It might even be so dim it's hard to see. The light didn't change, but your distance changed. And as your distance changed, its intensity changed. When we think about light's intensity diminishing or decreasing with distance, we can also think about sound. Sound behaves the same way. Things are quieter when you're further from them. And also a lot of different things. And one of the best analogies we can make is actually a spray can. This sprayer produces a mist of water, not light or sound. But it's a good model for the inverse square law. You can see when I push on the top, a fine spray of water comes out. Now we can see how much water is in any given area using a cloth like this one. If I hold the sprayer a long distance from the cloth, so that would be close, I'm coming far away from the cloth and I spray, the cloth doesn't really change color. But if I hold it right up next to the cloth and I spray, you can see that there's an awful lot of water in a very small area. All right, the reason we saw that spray can spraying water is because it's a good example or metaphor or model for light. A light bulb is spraying out photons, particles or little chunks of light. If you're really close to the light bulb, you catch a lot of them. If you're further away, you might catch a lot fewer. Let's take a look at this example. I like this one a lot. Here we've got different squares at different distances from a source or S of light. This first square is a distance of r away from the light. And we can see that it's being hit by 1, 2, 3, 4, 5, 6, 7, 8, 9 photons. Now we're going to step back until we are now at a distance of 2r from the light. Well, look, we still have the same 9 photons. 1, 2, 3, 4, 5, 6, 7, 8, 9. But they're not all hitting in the same area. This area A is the same as this area A. It used to be hit by 9 photons. Now it's only hit by 3. So it's going to experience a dimmer light. Step back another unit of distance to 3r, and you can see we still have the same 9 photons, but now they're being spread out over an area that is 9 times larger. Mathematically, this looks like this. At the distance r, we have an intensity of 9 dots per unit. At a distance of 2r, we have an intensity of 9 dots for every 4 units. We'll call that I over 4 because it's the same intensity divided by 4 units. At a distance of 3r, we have an intensity of 9 dots divided by 9 units, or I over 9. A key idea here is this. We went from 1 to 1/4 to 1/9, the intensity. And when you see a progression that involves 1, 4, 9, perhaps you're going to start thinking mathematically, and perhaps you'll realize, oh, 4 and 9, those are squares, right? And that's what we're seeing here. We have intensity over 1 squared, where 1 is the distance from the source. At a distance of 2, we have intensity over 2 squared, or 4. At a distance of 3, we have intensity over 3 squared, or 9. So as you step away from a source, the intensity of the light it's producing decreases according to the square of your distance away from it. And mathematically, this happens because light is radiating in a spherical pattern, and the area of a sphere is 4/3 pi r squared. What it means practically is that things get less bright as you get further away, or that intensity decreases with r squared. The formula looks like this. If you want to know the intensity of a light at a given distance, we're going to call that distance r. We're going to call the intensity I, and we're going to need to know the power of the light, which we'll call P. At a distance of 1 meter, intensity at 1 meter equals the power of the light divided by 4 pi, 1 squared. At a distance of 2 meters, intensity at 2 meters equals power of the light divided by 4 pi, 2 squared, because the area of the sphere at 2 meters is so much larger. You can see that you have 1/4 the intensity as you get only 1 meter further away. Let's make it practical. You turn on a 250 watt light bulb, that's a bright light bulb in a room, and we want to know what intensity of light you find as you get 4 meters away from it. Well, remember our formula. We need to know a distance, which we'll call r, and a power, which we'll call p, and we need to then calculate the intensity. Intensity is going to be equal to power divided by 4 pi r squared. Please pause me now and solve this problem. Do your best. It's okay if you're wrong. Go ahead and pause now. And welcome back. Let's see what you did. We have a power of 250 watts and a distance of 4 meters. If for any reason you haven't done it yet, please plug those numbers in and solve. That leaves us with 250 watts divided by 4 pi, 4 squared, or 250 watts divided by 64 pi meters squared, or 1.24 watts per meter squared. So you've got a 250 watt light bulb, but as you get further and further away, you have fewer of those watts per every meter squared. Today's big ideas were that intensity decreases with the square of distance to the source. I can't wait to see the work you do on this.